The broadcast is now starting. All attendees are in listen-only mode.
In today's session, we are going to talk about improving the efficiency of transformer testing. My name is Sanket Bolar, and I am an applications engineer with Megger. I started off as a testing engineer in the transformer industry. Then I did my master's in electrical engineering with specialization in power systems. And I've been working with the technical support group with Megger in the Dallas office for a little over a year now. In today's presentation, we're going to start off with what is a transformer. Then we're going to list the field tests done on a transformer. We're going to briefly cover each test, and then eventually we're going to discuss ways and means to test a transformer by taking less time and effort. This is the most simplistic representation of a transformer. You have two windings wound over a core. The windings represent the electrical circuit and the core represents the magnetic circuit. When you apply an AC voltage on one of the windings, an alternating flux is set up in the core, and this flux causes an EMF to be induced in the other winding as well. The EMF induced per turn is the same, so the voltages induced in both the windings are proportional to the turns of the windings. The assembly is placed inside a tank. The tank is grounded, and in this case it's filled with oil. Field tests done on a transformer. You have turns ratio, winding resistance, insulation resistance, capacitance, power factor, excitation current, sweep frequency response analysis, leakage reactants. The standard that deals with field testing of a transformer is C57152, and all these tests are mentioned in the standard. Before we get into the tests, we need to take a look at the nameplate of a transformer, because when we step out into the field to test a transformer, we need to know what kind of a transformer we are testing. The nameplate of the transformer contains some important information which is really useful. So let's go over the nameplate of a transformer. Starting off from the top, at the top of the nameplate we have the cooling class of the transformer. Here you can see it's ONAN and ONAF. ONAN stands for oil natural, air natural. Oil natural means that the flow of oil in the tank is natural, that is by the process of convection. Air natural means that there are radiators on the tank. Air forced means that there are fans on the radiators. There are two ONAFs in there. The difference between the two is the number of fans in operation. When the loading on the transformer increases and the temperature increases beyond a certain point, additional fans are switched on into operation. It's a three-phase transformer and the system frequency is 60 Hz. You have the continuous temperature rise. There's 55C and 65C. Continuous temperature rise is the winding rise at which the transformer can operate continuously. There are two MVAs which correspond to one set of MVAs correspond to 55C, the other set correspond to 65C. Rated high voltage is 69 kV, rated low voltage is 12.47 kV. It's a Y-connected winding, so you have the line-to-line voltage as well as the line-to-neutral voltage, which is 7.2 kV. BIL stands for basic impulse insulation level. It's 350 kV peak for the high voltage winding and 110 kV peak for the low voltage winding. The impedance value of the transformer is punched on the nameplate at 7.56%. Moving to the lower half of the nameplate, it tells us how the windings are connected inside the transformer. We can see that the high voltage winding is a delta and the low voltage winding is a Y-connected winding, then accessible neutral. The vector diagram of the transformer tells me that its vector group is DYN1. I'm not going to discuss how you can um, you would be able to make out what the vector group is by looking at the vector diagram. But what I'll tell you is that if you look at the vector diagram of the transformer, the low voltage winding A phase is X1 XO. The side of the triangle parallel to X1 XO is H1 H3, which tells me that the top of the A phase winding on the high side is connected to H1 bushing and the bottom is connected to H3. So the A phase lies between H1 and H3. Similarly, the B phase lies between H2 and H1, and the C phase lies between H3 and H2. This can be verified by looking at the diagram given on the left. We see that the top of the winding is connected to H1, the bottom is connected to H3 for the A phase. Alright, starting with the first test on the list that we saw earlier. Turns ratio test is a basic check to see whether the transformer is performing its primary function, which is transformation of voltage from one level to the other. Turns ratio is verified by applying voltage on the high winding, which is the winding with more number of turns, and measuring the induced voltage on the low winding. Measured values should be within plus minus 0.5% of calculated values. How are the values calculated? We look at the rated voltages, the tap voltage is given on the nameplate, and we calculate the values on a phase by phase basis. And that's the reason you see a factor of square root of 3 there. It's because the low voltage winding is a Y connected winding, and since we are looking at the phase voltages, we need to look at the line to neutral voltage and not the line to line voltage. That's the reason we divide the line to line voltage by a square root of 3 factor. This is what the circuit looks like. So you apply an alternating voltage on the winding with more number of turns. You measure the voltage on the winding with less number of turns. You compare the measured values with the calculated values. As you can see, and as I told you earlier, the EMF induced per turn is the same on both sides. So the ratio of voltages is equal to the ratio of the turns. Winding resistance test. This test is done at the factory to calculate the copper losses. During load loss measurement calculations, we differentiate the losses into copper losses and stray losses, and that's where the resistance measured comes into the picture. Test is also used to determine the winding gradient as part of temperaturized calculations. Winding gradient is the difference between the winding temperature and the oil temperature. This gradient, which is calculated, is used to calibrate the winding temperature indicator gauges. So the WTI gauges that you have, the conventional ones, they measure the oil temperature, and the gradient is added to the reading so that the gauge displays the winding temperature. On site, this test is primarily done to check for loose connections, shorted turns, and tap changer contacts. Winding resistance is measured by injecting DC current into the winding. Measured values are corrected to a reference temperature. Resistance is a temperature dependent variable. If you do the tests at two different temperatures, you'll get two different values. So the values need to be corrected to a reference temperature for comparison. The formula that you see on the slide, RS is the reference, is the resistance at reference temperature. RM is the measured resistance. TS is the reference temperature. Tm is the temperature at which the measurement is done, and Tk is the temperature coefficient, which depends on the winding material. It's 235 for copper, it's 225 for aluminum. Percentage winding difference between phases should be less than 2%. So at a particular tap, you should not see much difference in values among the three phases. Percentage difference between factory and field data should be less than 5%. Demagnetizing the core is very important, as certain test results can get affected by residual magnetism because of DC injection into the winding. This is the circuit for winding resistance test. You have a DC source through which you inject DC current into the winding. When you inject DC current, you end up saturating the core. The inductance part of the winding collapses, and what you're left with is the resistive voltage drop. You know the current that you're injecting into the winding. You're measuring the voltage drop. By using the Ohm's law, you get the resistance of the winding. The next test on the list is measurement of insulation resistance. This test is done to check the health of the insulation. A DC voltage, typically 5 kV or 10 kV, is applied across the insulation, and the insulation resistance value is measured after 1 minute. There are 3 tests done on a transformer: high to grounded low, low to grounded high, and high to low. This is for a 2-winding transformer. And when I say typically 5 kV or 10 kV, I'm talking about high voltage transformers. You cannot be applying 10 kV to a 5 kV transformer. So you need to apply the appropriate voltage. The voltage that you apply should be less than half the AC withstand voltage of the transformer. This is what the circuit would look like. So you short the, for any insulation test, be it power factor or insulation resistance or AC withstand test for that matter, you always short the bushings of a winding. So you short the high bushings and then you short the low bushings separately. This is done to keep the winding at a uniform potential throughout. So you have 2 electrodes inside the tank. One's a high, one's a low. In the power factor test, AC voltage is applied across the insulation and the losses are calculated. Power factor or dissipation factor is expressed in percentage, and that's used as an indicator for the quality of the insulation. Test is done on bushings as well. This is a table from the standard which shows you the power factor limits for new transformers and for service age transformers. And on the right you can see the circuit. So you have the power factor test set. The setup on the transformer would be the same. So you have the high bushings shorted, the low bushings shorted separately. When you do this test on a 2-winding transformer, you measure 3 capacitances. You measure the high to low capacitance, which is the interwinding capacitance, and you measure the high to ground capacitance and low to ground capacitance. Depending on what capacitance you want to measure, you would select the appropriate mode of measurement. So for interwinding capacitance, you would use the UST mode. For interwinding plus winding to ground, you would use the GST mode. And just for the winding to ground capacitance, you would use the GST-G mode. For bushings, this is what the circuit would look like. So you would connect the high voltage lead on the stem of the bushing, and you would connect the measurement channel on the test tap of the bushing. In a bushing, you have 2 capacitances. One is C1, which is the capacitance from the conductor to the test tap of the bushing, and C2 is the insulation from the test tap to the ground. To measure C1, you would use the UST mode. To measure C2, you would use the GST-G mode, and you would swap the leads. So the high voltage lead goes on the test tap of the bushing, and the measurement channel goes on the stem of the bushing. The voltage that you use for measuring C2 would be much lower. It's typically done at 500 volts or 1 kV. Excitation current test is done to look for interturn faults and to check the condition of the core. Excitation current is the current drawn by the transformer in the no-load state. High winding is energized at a suitable voltage and excitation current is measured. When I say suitable voltage, it means that the voltage that you apply cannot be greater than the rated voltage of the transformer. Results can get affected by residual magnetism in the core. So if the core is magnetized and if you do this test, then you can get different results. So we need to make sure that the core is demagnetized when we do this test. The condition of the core determines the value that you get. So you would get high values if the core is in a bad shape. Any interturn faults will cause the current to shoot up. This is what the circuit looks like. You apply an alternating voltage on the high winding with the low winding open circuited. Sweep frequency response analysis. This test is done to check the mechanical integrity of the insulation. This is the last test done at the factory and the first test done on site. When the transformer is made at the factory, after all the electrical testing is done, this test is carried out, and when the transformer lands at the substation, this is the first test that's done. The results are compared, and any deviation tells the customer that the mechanical integrity has been compromised. The transformer may have sustained some shocks during transport. So that's the primary objective of this test. To look for any physical damage that may have occurred inside the transformer, any physical shifting or deformation. A variable frequency low voltage signal is applied at one terminal on the transformer, and the response signal is obtained from another terminal on the transformer. So sweep is done over a wide range of frequencies, and you get a unique signature Bode plot. When I say signature, what I mean is that it's unique to every transformer. Even two sister transformers, that is, transformers having the same design, would display certain minor deviations in the same type of measurement curves. A wide range of problems can be detected by analyzing differences in SFRA curves. Different frequency ranges correspond to different problem areas. This is what the measurement circuit looks like. So you have a set of leads for applying the signal, you have a set of leads for measuring the signal. It's a single phase measurement, so you don't have a three-phase set of leads. This is a sample plot, so you have a magnitude plot, you have a phase plot. The magnitude is expressed in decibels because the output signal varies over a wide range magnitude-wise. The phase plot tells you the nature of the signal that you're getting out of the transformer. That's whether it's inductive or capacitive. The points at which the slope of the curve changes. For example, if you look at the lower frequencies of the magnitude plot here, you can see 2 points. So the points at which the nature of the curve changes from inductive to capacitive and vice versa are called the resonant frequencies. As I said earlier, different frequency ranges correspond to different problem areas. SFRA does not give you a proper conclusion. It doesn't tell you what exactly is wrong with the transformer. It just points towards a particular problem area, and then you need to do additional tests to determine what exactly is causing the deviation. Measurement of leakage reactants. Test is done to detect damage in the winding. So when you apply alternating voltage, a flux is set up, and that flux links with the secondary winding, causing a voltage in the secondary winding. Not all the flux that is set up in the primary links with the secondary winding. The flux that doesn't link with the secondary winding is called the leakage flux. And that leakage flux causes the transformer to have a reactance. Leakage reactance is the percentage of rated primary voltage required to circulate rated current in the shorted secondary winding. So if I apply AC voltage on the high winding with the low winding short circuited, the voltage that's required to circulate rated current in the windings of the transformer is called the impedance voltage. That impedance voltage expressed as a percentage is called the leakage impedance or leakage reactance. Test is done in the factory at much higher currents, uh, preferably at the rated current or a certain percentage of the rated current, and the values are punched on the nameplate. So everything that you have on the nameplate is determined beforehand, except for the impedance values which are punched on the nameplate after this test is done at the factory. On-site, single-phase tests are carried out. So there are two methods of doing the test. There is three-phase equivalent method and there is a single-phase method. If you do the three-phase equivalent method, then the value that you obtained should be within plus minus 3% of the nameplate values. If you do single phase tests, then the values that you obtain should be within plus minus 3% of the average of those three values that you get. Test is done by shorting the secondary winding and applying voltage on the primary so that a certain current flows in the primary, as I said earlier. So this test reflects the geometry of the circuit, the physical condition of the windings. So any winding deformation will cause a deviation in the leakage impedance. Now that we have covered all the tests, let's look at ways to improve efficiency. As regards turns ratio test, a lot of time can be saved by using an instrument with a three-phase set of leads. If you're using a single-phase instrument, then knowing the vector diagram uh, is always helpful, because you will know if it's a delta winding, you will know exactly where to connect the leads. If you're using a three-phase instrument, the instrument does that for you if you select the right vector group. So interpretation of vector diagram is important, and you need to know the values beforehand. Uh, you need to know what the calculated ratio values are if your instrument doesn't have a software that computes those values, because this test is all about comparing the measured values with the calculated values. So you need to know if the values fall within the plus minus 0.5% tolerance limit. For the winding resistance test, again, it helps a lot if you're using a three-phase, if you're using an instrument with three-phase set of leads. Again, if you have a single channel or a single phase instrument, then you should be able to interpret the vector diagram, and you should know where to make the connections. Selection of appropriate test current is very important. The current should be close to 10% of the rated current. If the current is too low, then it will result in more time for core saturation. If the current is too high, it may cause the winding to get heated, and you may get erroneous results because of change in temperature of the winding. So you need to make sure that you select the appropriate current. One way of reducing time by a little bit is connection of leads to ensure quicker magnetization. And this method comes into play when you're using a single phase resistance test set. So you need to take advantage of the direction in which the core is magnetized. if you do the test on phase A first, you do the test from H1 to H3, and here we are looking at a D1 transformer. So the A phase is between H1 and H3. When you do the test on phase A, you magnetize the core in a certain way. When you move on to phase B, you don't test it from H2 to H1. You instead you test it from H1 to H2, and you will get the reading slightly quickly because the core is already magnetized in that particular direction. So use the direction in which the core is magnetized to reduce the time required to obtain a stable reading. Use dual channels to test two phases at the same time. This method can be used when you are using a single phase resistance test set on a Y-connected winding with an accessible neutral. So what you will do is you will connect if your test set has two voltage channels. What you can do is connect one voltage channel across one phase, connect the second voltage channel across the other phase, and inject the current from one phase, take it out from the other. You typically do it on A and C phases together. So A phase lies between H1 and HO. You inject the current into H1, and you connect the other current lead to H3. The current goes in from H1, goes out from H3, and you measure the voltage drops between H1 and HO and HO and H3. So you end up getting two readings at the same time. And then you run through the whole range of taps, and once you're done with the measurements for A and C phase, you switch the leads to phase B and you do the test again at all taps. Dual winding resistance measurement causes faster stabilization of the readings. The rate of magnetization depends on the turns of the winding, depends on the ampere turns. So when you bring the high voltage winding into the picture, you amplify the number of turns in the circuit, so you cause faster magnetization uh, by that much. So adding the high voltage winding in series to the low voltage winding really helps uh, as far as faster magnetization is concerned. It reduces the time required for stabilization. This is helpful especially in cases like generator transformers, where just connecting to the low voltage winding may cause a long time, may result in a long time required for stable readings. Using leads compatible with both turns ratio test set and winding resistance test set. Uh, so if you have two test sets if you have a single set of leads which is compatible with both, what you can do is start off with the turns ratio test, and once you're done with the test, just switch from the TTR test set to an MTO test set or winding resistance test set, and do the winding resistance test. So it'll be a one-time connection thing. Just make the connection at the start of the test, and you're able to do both tests without you having to climb up and down the transformer. So it saves a lot of time. Switching between instruments if you're not testing on all taps. Turns ratio test, for example, we have a 33 tap transformer and we don't want to measure the ratios on all taps. What we can do is we can start off at tap 1, do the turns ratio test, switch from the TTR to the MTO, do the winding resistance test at tap 1, then move from tap 1 to tap 17, testing on each tap as we go. Then we can switch over to the TTR test set, do the turns ratio test at tap 17, then switch back to the MTO, and then test from tap 17 to tap 33. And then at tap 33, we can switch back over to TTR test and do the test tap 33. One way of saving time is by doing the insulation tests together. So we do the insulation resistance and power factor test one after the other. The setup on the transformer is the same for both tests. The high bushings are shorted together and the low bushings are shorted together separately. As far as power factor is concerned, some time can be saved by testing two bushings at the same time. Uh, this method is especially useful while testing auto transformers, where you can have as many as 7 bushings on a single winding. So you'll have the 3 H bushings, you'll have the 3 X bushings, and you'll have the neutral bushings, neutral bushing. As far as the test sequence is concerned, you can move around sweep frequency response analysis. You can either do it at the beginning, or if it suits you, you can do it at the end. Uh, if you're using a three-phase, uh, if you have a TTR and an MTO with a compatible set of test leads, it makes sense to do the turns ratio test and winding resistance test together. Insulation tests, since they require the same setup, you would group them together. Since most power factor test sets have an excitation, can be used for excitation current test, that test naturally comes after the power factor test. And the leakage reactance test, if you're using a separate instrument, uh, doesn't matter, or if your power factor test set has that feature on it, well and good. But leakage reactance can be done after the excitation current test. So this is what it would look like if I were to represent everything in a simplistic format. This is what the sequence would look like. I would start off with the sweep frequency response analysis, get done with that. Then I move on to the turns ratio test. This is the circuit for the turns ratio test. Once I'm done, I switch over from the TTR test set to the MTO test set, and I do the winding resistance test. Then I move on to the insulation tests. So I would short the bushings of the windings. Then I would connect an insulation resistance test set to it. Once I'm done with the insulation resistance, I switch over to a power factor test set, do the power factor test, and then take off the shortings and the bushings. Then do the excitation current test. And once I'm done with that, I'll short the secondary winding and do the leakage reactance test. If you follow this sequence, you will take less time and effort, and hopefully most of those tests uh, will help you save a lot of time and effort. This is my contact information. For any sales related information, you can contact sales. Uh, any feedback that you have, you can fill out the survey. That would be helpful. Thank you.